So we've already looked at reactions in general. We know our 5 basic types of reactions, and what we want to do is focus in on a couple of those types of reactions a little bit more specifically and see what else they mean for us and what else we can do with them. And today we're going to start with single displacement reactions. So the basic pattern on a single displacement reaction is what you see there. And that's sort of the most normal, most common one that we are going to use, where the element and the first thing in the compound trade places, so A and C. But it can also happen, so I'll give you a couple of examples of that, using also hydrogen, and I tossed a carbon in there because once in a while that shows up as well. But the other thing that will happen once in a while, and honestly I don't want to put it up here as a completely different kind of example, because if you just think things through about what you know about chemistry so far, it should just make a whole lot of sense that if you had a metal non-metal compound and another non-metal coming in there as an element form, then you could have the non-metals trading places, and it wouldn't really be all that surprising. And as an example, we've got sodium bromide reacting with chlorine, where chlorine pushes the bromine out of the way and takes over. So what I want you to do is I want you to write these examples down. I want you to pause the video and I want you to predict the products. And we already know how to predict the products. Perhaps the last one is a little bit fuzzy just because there's a couple of things that maybe we don't know completely yet, but do your best. Now hopefully you did pause the video and hopefully you've got some products predicted. If you didn't, well, I mean, I guess eventually you'll get an opportunity to show me that you can do it. And again, as I mentioned, the last one, you might have something slightly different simply based on things that you may or may not know about, well, based on nomenclature, because nomenclature is one of the things that we use to help us predict products. But that's not really the purpose of this video. The purpose of this video is to dig into single displacement reactions a little bit more and to not just predict the products, but predict whether or not those products will actually form. So I want you to take a look at these two reactions and answer the question of what do you notice about them. And if you went through the process of predicting the products, and perhaps even if you didn't, you might have noticed that the reactions are effectively the reverse of each other. In other words, the products of the top reaction are the reactants for the bottom reaction. And that actually should generate a couple of questions for us. Number one is, are both of those reactions possible? And what I mean by that is not, could we write both of those reactions on paper, because clearly we can write both of those reactions on paper, but could they both happen for real? The second question that needs to be asked is, are both reactions spontaneous? And we'll get to that in a bit more detail in a second. But the third question is actually going to be the focus of what we do in this video, and that is, how could we predict if one of those reactions is not possible or is not spontaneous? Are there tools at our disposal to help us predict yes or no? But so we come back to that spontaneous business. So a spontaneous reaction is a reaction that is going to occur without the constant supply of outside energy. And probably one of the most obvious examples you have of that is a fire. You need to light a fire, but once that fire is lit, hopefully it keeps burning on its own without being constantly lit. Yes, we've all tried to make fires with wet wood, and it doesn't work out so well. But in an ideal circumstance, once you hit the match to your paper, the wood, whatever it is you're burning, it keeps going. You don't have to keep using matches. If you think about a battery in some rechargeable device like a phone, okay, once you turn on that phone, the battery is going to supply the electricity all by itself. You don't have to shake it, do anything special to it. It's going to constantly supply that electricity to the device until it runs out. And then what happens? Well, then you have to plug the battery in. And the battery will only recharge if it is plugged in. As soon as you unplug it, it stops recharging. So the discharging process is spontaneous. The recharging process, where you're putting electricity back in, spoiler alert, that's not actually how it happens, but for the purposes of this, as you're putting electricity back in, that is a non-spontaneous process. Both processes are possible, but only one of them is spontaneous. So if we go back to those two reactions that we were looking at and the questions we asked, are both reactions possible? Yes, both of those reactions are possible. Are both of those reactions spontaneous? No. Only one reaction will be spontaneous. As soon as you know which one reaction is spontaneous, which one will happen all by itself without the constant supply of outside energy, that automatically means the reverse reaction is non-spontaneous. In order for that reaction to happen, you would have to supply the energy. It's like a battery. It's going to discharge all by itself, spontaneous. It would only recharge if you plug it in and supply the energy back. Okay, but how about this last reaction about how could we predict? Well, that actually becomes the next thing. You will find in your textbook in a couple of different places, but probably the quickest one, and the one that's right around there, is on page 165. It's called something called the activity series of metals. The one in your textbook is a bit different from this, but more or less the same thing. It lists a bunch of metals from most reactive to least reactive. It's the most common way you'll see that list, but it could be the opposite. And it'll throw hydrogen in there. Sometimes it's not really in the middle, but it'll throw hydrogen in there somewhere in the middle. And then the idea is that metals that are higher than hydrogen will react with hydrogen or something like that. We'll get to that in a little bit. And metals that are below that will not. And if you want to think about this in a metallurgy, history of civilization kind of way, gold, silver, and copper are metals that can be, particularly gold and silver, can be found in nature in their pure form. All the other metals need to be found, or are found in mineral form, in some kind of compound form, and then need to be refined. Okay, so how do we use the table? Well, the short version, and okay, you're right, that's not a very short version of the story, is that the more reactive metal is going to be in compound form and the less reactive metal will be in elemental form. And what I mean by that is if I have a possible single displacement reaction, then the more reactive metal will be the one that ends up in compound form, and the less reactive metal will be the one that ends up in elemental form. In other words, compound form, that element has reacted. In elemental form, that element has not. So the more reactive element will be in the compound, in the reacted form. So if you take that reaction and you find that on the table, you'd first find iron and find zinc. And you find that zinc is higher on the table than iron. That means zinc is more reactive than iron, and I realize it's redundant, but I had it in brackets, so you might have skipped it. That means zinc is more likely going to be in compound form, which means in this particular reaction, where iron starts out in compound form, it's going to be bumped out by zinc, and zinc will take over the job of being in compound, leaving iron, less reactive metal, to be not in the compound. So that reaction, as written, is spontaneous. It follows the activity series. If we look at another pair of metals in a reaction, so yeah, I got lazy. All I did was change Z to S, but same kind of thing. I find those two metals on the table. There's iron still, and now I found tin just below iron. Well, tin, Sn, is lower on the table, which means it's on the less reactive side of the table than iron. That means tin is less reactive, which means it's less likely to form a compound. That means Sn, tin, will not be in the compound form. Iron will. Well, not only that, but iron already is in the compound form in that reaction, which means that reaction, as written, will not be spontaneous. It will not form the products, even though I could write the products on paper, even though those products are possible, they're not going to be spontaneous, because all by itself, without constant supply of energy, iron is more likely to be in compound form, tin is more likely to be in elemental form. Okay, how about explaining that? Like, not only now we can predict it if we have an activity series, but what is that based on? Is there something else behind that? How do we explain it? Well, I want to work toward that, but that's something that's more of a class, followed on by a lab, followed on by more discussion. kind of thing, but we'll see how we can do with that, or what we can do with that. But I want you to, as a bit of a look ahead, or getting ready for that time when we do work on it, ask yourself the question, what is actually happening to the atoms at the atomic level? So I've got iron in a compound with chlorine, I've got zinc on its own, but what's actually the atoms doing? Think about bonding, think about the kind of bonding, think about what has to happen in order to make those bonds happen. Think about even the nomenclature, what's going on in those kinds of things. And that might be a bit of a clue as to how, or what we're going to use to help us explain what's going on. All right, to wrap things up, these are the things that we've talked about in this video. These are the kinds of things you should be able to do at this point. I know I've kind of given you a little bit of a look ahead to what's coming up a little bit later, but at this point, these are the things you should be able to do. And then we'll talk another time.